information of all the product are given on the web page. If we talk about the publication, you can go to the research option and go to the publication options, where you can find all the publication and collaborations. For this LAOSS, you can see I can go to this LAOSS and click on references. So you can see this is a reference option where some people are using, like Swansea University, they are using, and bottom of that you can find the publication on electrical crosstalk effect between different pixel. You can find this investigate papers, research paper, recent research paper on investigation of electrical crosstalk between different picture with high resolution or unique LED and micro display applications, including the solar cell application as well, and with different near infrared sensitive optical image sensors applications, perovskite solar module application design and optimization. This paper is there, some thesis. Color gamut changes by optical crosstalk in high resolution OLED, and some organic photovoltaic application for indoor applications. So these are all research paper. You can look into the papers later this presentation demonstration, so that you will find many more things. You can see these are some modeling crosstalk or quantitative pixel crosstalk in AMOLED display or electrothermal simulation of large area device application. This is just for your kind information that all the information are available. So in details, you can look into our web page. And even YouTube channels are there where you can find some videos as well related to Fluxim LAOSS. So these are some research that videos are available. Once you will click on it in the form of videos, something you can find it related to around 9 papers, 9 videos are there. So you can look into these videos information. You can see these are all related video with this LAOSS and other sets of applications. Now I would like to open the software. You can see my screen, LAOSS 5.4.1. So I would like to right click and open as an administrator to give my background permission privileges. Now this is a graphical user interface of this LAOSS software. It is a completely user interface based tool. So there is no coding is required, where you have no need to write any code or any script in the software. So you can find this user interface very easier or easy to learn. You will not find any difficulty. Either you are beginner or you are expert in the kind of software field. Apart from that, there is a help option are there where you can find some manual and tutorials. Manual, where you will find the background physics, background models, background equations, on what equations the software will predict the device characteristics, what models are using, what equations are using, that are well explained in the manual page. So I click on this manual, you can find this is a LAOSS manual. Even after this webinar, those who are interested, I can share you this manual and tutorial link to all of you, so that you can explore in the details, or if you will install the software, by default you will also get this manual and tutorial wherever you will install this LAOSS software. So this LAOSS is basically, as you already know, for design, optimization, simulation of large area, solar cell, OLED, module, PV, crosstalk and array applications. For background physics equations, you can see how much the electrical model, thermal module. So I can go down and step by step all the information are given. Either you want to take the information about physics equations or you want to take the information about how to proceed to create different device structures or meshing. So you can see this is a one by one user interface information where anybody can go down and find, follow the step by step procedure and easily it can be created. So within week you can easily learn the capability of this tool. So the some topography view you can also import or generate or load in the object parameter file, some 3D Max file, DXF AutoCAD file, object file, STL file, and some different other extension you can import and export in the tool. You can see these are different geometry tapes so that you can get more light absorbed in your device study. Micro lenses array can also be simulated. That's why you can see the cylindrical array in topography import, spherical lenses and other characteristics, and you can do the geometry of your device, predefined pixel topography, and so many things are there. You can see this is generate pixel structure in topography import. Basically, to create the geometry, there is a software called LaborCAD. LaborCAD. This LaborCAD is basically an open source tool which will help to create the geometry. Open source tool where anybody can download and create the geometry of your solar cell. And that geometry can be uploaded in this LAOSS. Now you can see, apart from manual, tutorial option is there. The difference between the tutorial and manual is, manual will give you the background information. Tutorial will explain you the step-by-step procedure where you can create different kind of solar cell device simulation from scratch. So step-by-step procedure for creating or designing, modeling of the solar cell and do the simulation till the visualization of your output. That can be seen in the tutorial package. So that's why this tutorial package where proper screenshots are there, and I believe the user will get very easier once you will explore it or you will become familiar with this LAOSS tool. So you can see I can go up where couple of steps are there. If you want to simulate your first OLED, you can simulate your first OLED. You can import your geometry in the LAOSS, first PV simulation, first maybe PV module simulation, or case studies are there for OPV, AMOLED pixel crosstalk, optical crosstalk, and non-uniformity of emission in OLED lighting, OLED electrothermal simulation, solar concentration, electrical and thermal simulation. These are all tutorials. You can see how to create the geometry in lever tool and this type of geometry. You can see this is a hexagonal metal grid, and this hexagonal metal grid can be created for the for the geometry of your electrode. And if we can minimize the light reflection by using the electrode design, we can have multiple options to create a suitable geometry of your electrode so that the losses can be minimized and you can find the potential distribution inside it. So this DXF file of the geometry can be created in any CAD tool and you can import in this LAOSS. This is a first example where if you want to simulate the first OLED, the everything starts from the geometry section where geometry of the device need to be created. Whatever wafers are there, whatever next depositions are there, or whatever implantation need to be done, or contact formation need to be defined, or biasing voltage you need to define. These are step-by-step procedure need to be done. That's why the first solar cell, first LED or pixel crosstalk, it can helpful create all of them in single tutorials. You can see, just follow it and you will be able to help. It will help you a lot for creating any kind of complex structure. Still, if you will have any problem, you will face any problem, you can also interact to us. We can help you so that you will understand your desired goal by using this tool. Now I would like to show the demo. In the demo part, you can see there is an option called new project. You can start from scratch or you can also load the project from the library. If you want to start from scratch, you can click on the new. And here, once you will click on the new project, you can select either you want to create the project of your large area devices or you want to start with the ray tracing applications. Accordingly, it will select the default path or you can set the custom projects. You can set the name of project and select the location of your project where you want to save your project applications and click on OK button. Once you click on it, you can find this is called the feature which the user need to give as an input. In this you can see the geometry and meshing, device IBT, that is second feature, second tab. There is electrode tab is there. There is boundary condition, ohmic type, Schottky type, or any different type of boundary condition. Swapping and optimization, where minimum and maximum of your swap value, variable value can be defined. Let's suppose you want to swap the thickness, then minimum and maximum you can set in the software. Software will perform the simulation on each and every biasing and it will show at what particular bias voltage or whatever input you have taken, at that particular input value you are getting the good output for that particular problem. So that's why the sweep option is there. There is option called optimization, fitting and optimization. You can fit the global fit optimization is there, local optimization algorithm is there. So this algorithm, I believe it will optimize your device structures. And there is solver are there which will solve your equations. Fully solver, simultaneous solver, direct solver or direct spare solvers are there. Global solvers are there, non-linear solvers are there. Newton solver with line search, Powell dogleg, Leavenworth, Marquardt and path continuation. These are different non-linear solver that will solve the device theoretical models equations. So user can define as per the convenience. If I click on this geometry file, you can see the geometry need to be given either in the form of DXF, in the form of UNB Salom. There is a predefined rectangular geometry there, metal finger geometry available, metal strip geometry is available, rectangular metal grid, hexagonal metal grid. This is predefined geometry that already is available. DXF geometry file you can upload. It can be created by either in the CAD file or even in our software LibreCAD. that is open source tool where you can also create the geometry. And this allow UNB format, some different wireless inside tool is there where some UNB application label, it can also get the input data. So for DXF file, select the DXF file and click on file option. Once you click on file option, since my software is installed in C drive, program file, FluxSim and LAOSS, this is a part of my project. I would like to go to the example. In the example, you can see the geometry need to be required. Either you can create from scratch in the LaborCAD and export in DXF format. That is freely available. If you don't have any LaborCAD tool, it can simply be installed from the website and anybody can install it. Even I can also help you to install the LaborCAD applications. Once you install the LaborCAD, then you can find this is called DXF file. It is called the geometry file of your device applications. So either you can take this 02 millimeter DXF file, 10 cross 10 centimeter DXF file, or hexagonal 100 cross 100 millimeter DXF file. Let's suppose I want to take this hexagonal 100 cross 100 millimeter dot DXF file. It's a simply a geometry file, so it can be uploaded. I can click on and click on open. Now you can see in this right side, sorry, the geometry of the hexagonal DXF file that is created maybe in CAD tool or maybe in this our software, LaborCAD. So here you can see this is called geometry. It is geometry. This is a geometry that you can see here. I can move it. I can click on the show geometry, that will show you the geometry. So 0 to 100, 0 to 100. So 100 meter by 100 meter. This is geometry of your device. And the geometry is taken from the library. Now, if you want to simulate it, you can see there is predefined geometry is given. That's why the feature show geometry is not given. Now to generate the mesh, there is a meshing tool that is called NetGen and BAMG. This is basically a mesh generator which will generate the mesh. Once the mesh is generated, NetGen mesh generator is there, and this BAMG is called bidimensional. I think anisotropic mesh generator is there. So I will select this mesh generator and then click on this run meshing. I can also set the minimum edge size or maximum number of vertices. It's called 50,000. So I click on this run meshing option. Mesh is going to be run. Mesh is running. It is in the progress. It may take very little bit time to generate or visualize the mesh in the geometry, hexagonal matter geometry. So if there is some problem, then we can also minimize, we can increase the minimum edge size and maximum edge size. And then the maximum number of vertices will be reduced. If the number of vertices are increasing, minimum edge, maximal edge are very low, then the mesh will take some time to simulate it. It depends on your computer configurations also. My configuration is little bit low, but anyway, when you will decrease this vertices number, then you will get a faster mesh generation. So let's wait for 1 minute, then I can take another example and try to show you the mesh and some other input parameters. You can see the mesh size was very dense. That's why the mesh is taking a lot of times. Let me increase this minimal age value. You can see the number of vertices that was previously 1 lakh or 11 lakh 36,911. That's why it was take a lot of time. So I have reduced the value from minimum age to maximum age size, and then I want to run the mesh. Now you can see the mesh has run because the number of vertices has been decreased around 17,597 mesh counts. So I can zoom it. You can see this is a max hexagonal metal grid, and this is triangular mesh. So hexagonal metal grid and triangular mesh is there. You can see this is around 34,765 triangle. If you want to simulate the mesh by using this anisotropic bidirectional mesh, then I can select and click on run button. This may be some different mesh, same triangular, but some size or some position may be different. So that's why two meshing tools are there. Now this is called mesh. Okay, once the mesh is done, then next you can see there is an option called device IBT. It means the electrode, thermal coupling, device type, or simultaneous simulation type, steady state, AC, and excitations. So I can select the single electrode. So either you can select the single electrode or the coupled electrode between single and coupled. And there is option called thermal coupling with thermal effect, without temperature or thermal effect, heat generation only, full electrical plus thermal, both modules are there, device OPV is there, and steady states and AC calculation, the results can come. And in the bottom of the page, you can find the electrical coupling in ohm, Montgomery, diode model, imported JVT. These are all results from one-dimensional as well as whatever third party other tools are there. I click on import JVT. Once I imported, you can see in the slide side, the color has been changed. The mesh has been assigned. Electrical thermal coupling is done. And then after applying the device IBT, current voltage, signal electrode type, thermal coupling or device
Excuse me, sir, you are not audible, sir.
Mic is mute. Sir, your mic is mute. See in the meet.
Sir, are we audible? Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Okay, fine. So here you can define, the how the device is formed. The device will start scratch from the geometry. Once the geometry is created, so how the geometry will be created? Either you can take the DXF file or you can take the default geometry given in the this LAOSS. And once the geometry is done, you can see these are multiple options for the geometry. The next geometry option is called meshing, where you can define the vertical mesh or that number of mesh points, node points, vertices can be defined. Then third type is called where you can set the electrode type, single electrode or coupled electrode, thermal annealing, thermal coupling or without heat temperature effect, and select the type of device, LED type or solar cell type, and steady state simulation, AC simulation. So DC, AC, transient all are there. You can see this is called, you can import the characteristics, import the, hello, you can import the one dimensional current voltage curve as well. You can see this is called import data, where from SAT you can import the JV data characteristics, not only from SAT from any tool. You can select it, import JV curve, and you can import your graph here. So the JV curve need to be imported here, and we have to select the file, then it will display. One minute. I will take in the example, and this is electrode type where top and bottom electrode, and more electrode if you want to define, simply you can click on this and you can restore your electrode type. And this is called where you can set the boundary, top edge of bottom edge of the boundary conditions. So if I select it, this first option, it will say here, this is called the red color bottom edge. It is called the bottom edge current type, and you can see called vertical red color edge. It is for the top device. Top, you have to assume it in the 3D. It is top device, left, bottom, or which edge is there for the top of the device. So that's why it is showing the direction on the top boundary condition. And this is sweep, where you can also do the sweeping and optimization, where you have to enable the sweeping. And you can add the sweeping here by clicking on this line, and you can define the input sweeping value. Either you are sweeping thickness, you are sweeping the voltage, current, or whatever input you will sweep, the select from the conditioner. Just a minute. One minute. Sorry. Am I audible?
Yes, sir.
Okay. So I would like to import some existing project. I go to the import from GIF file, and since the software location inside my C drive and Fluxim folder, and this LAOSS example, I will go there and go to the tutorial. This is existing tutorial. So for that, let me take one AMOLED crosstalk. I will open. It will load here. Now you can see here. And my screen is visible. Okay, perfect. So let me go there. So what I did, let me start from beginning. So I import the projects. I click on file and import from GIF file. So I want to take 2M OLED. I can take any solar cell also. So I click on open it, and let me overwrite with the existing project. So this is one pixel crosstalk where blue pixel will be there in in this geometry. Some of them are red pixel, some of them are blue pixel, some of them are green pixel. So DXF geometry file we have imported. It is in micrometer units. We can also define some defect or geometry we can create it. If I click on this device IBT, this is a coupled electrode device simulation with OLED type without coupling. If I select on this blue pixel, you can see this is red one. Vertical lines is called the blue pixel lines. This small one is called the green pixel lines, and third one is called the red pixel. This is called the red pixel box. So rectangular box is called red pixel. If you would like to visualize the graph, simply click on the blue pixel graph. It will plot the current density plot of this blue pixel. Similarly, for anything, you want to plot the green pixel or you want to plot the red pixel. So this graph you can visualize for current density, JV curve, and bottom of the page you can see here we have uploaded the IB of this red pixel, green pixel and blue pixels. There is an option called browse. In the browse we can browse the IB data. This is called JV curve of dark, light, green, OLED. Whatever data you want to browse for this data, it can be browsed. Unit and current density value you can plot. So under light or under dark condition, you can plot your device efficiency. And this is called electrode type. You can see this is electrode, default electrode. If you want to see the blue pixel electrode type on the top and bottom will also be there because it is not visualized in the 3D, it is 2D structure, but heat resistance are defined for 2D and 3D both. So these are all pixels. And for green pixel, once you select it, you can visualize it. And boundary condition, you can find the boundary condition for all the pixels either on top side or in the bottom side. The boundary conditions are set, that's why the color are changing respectively. And there is a swapping option is there where we are swapping the blue pixel voltage vising. It is swapping from 0 volt to 5 volt with the increment of 0.1 volt linearly. There is option called linearly, logarithmic or tabular. So it is swapping from 0 to 5 with 0.1 increment. So swapping will help you to optimize your device structure. Not only a blue pixel potential you can swap. You can swap the boundary condition, potential, temperature, electric current, thermal flux, or any other stack thickness, dark saturation current, ISC, conductivity, temperature. These are all input parameter swapping options where whatever the parameters are unknown for you, you can set the minima and maxima. And in between maxima and minima, you will find the more accurate characteristics. Software will give the simulation on multiple value between minima and maxima, and you can find the peak on exact particular value. That's why the blue pixel age, you can see the blue pixel potential are increased from 0 volt to 5 volt with an increment of 0.1. So software will do the simulation at 0 volt, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 up to 5 volt. It will run the calculation and you can find either you are getting the good output at 2 volt, 2.3 volt or 2.7 volt whatever the voltage you are getting the output, you can select it. And this is for optimization and fitting, global optimization or local optimization with imported JV curve, minima and maxima optimization. It is basically iteration control, which can control iteration and optimize your characteristics. And to select the solver, this is to select the solver and control the performance or memory trade-off by selecting the required features of the solvers. You can see there are some of non-linear Newton solvers, Newton solver with line search, Powell, Lindbergh, whatever the search option is there. Now I want to basically run the mesh and then we'll run the job. So simulation can be run from here. So before, since I run it in the morning, so I click on this result tab. This is result tab. So let me run it again. So by clicking on this run button, you can run the job. Now simulation is running, that you can see. The simulation is running. It will solving the equations. Software is very fast in converge. It will try to converge the equations default based on default parameter, and it will plot your output. You can see the result window has been enabled, and it has plotted the total device current diagram. This is potential that we have applied from 0 volt to 5 volt. So if I will zoom it, this particular point, it will increase from 0 volt. But you can see here, this one, at 0 volt, how much nearly you are getting the currents. Okay, and at what particular value the device current is like going down. So 0 to 5 volt we have given as an input, and you have to check at what particular voicing the device is going to be decreased. You can take the cursor on particular location and it will plot the potential as well as device current. So this is total device current. You can see with respect to x-axis, x log, y log, or in the form of logarithmic or without logarithmic also. This is without logarithmic. If you want to see the total ohmic losses, just click on this total top ohmic losses, and this is top ohmic loss output characteristics with respect to the changing of potential from 0 to 5 volt with 0.1 increment. That's why with the dotted lines are there. With every 0.1 increment, it is giving the dot, and you can take the cursor and it will give the value on that particular point. Now you can see this is global data. Here you can see the total device current, ohmic loss, top electrode, ohmic loss, bottom electrode. If I click on the solar cell, you can find the maximum power point, maximum power, open circuit voltage, since it is LED application, fill factor and other boundary condition flex and other things. For ohmic loss, bottom diagram, and this is for top diagram. For top and bottom ohmic loss diagram, you can see and check the variation in the losses to the top electrode and bottom electrode. That's why these two graphs are there. Source power diagram, once you click on it, it will plot the source power diagram. This is source power diagram. only since as an input we have sweep only the potential. So that's why the potential respect all output are plotting. This is total power diagram. Now you can see this is without any pixel. Okay. If you want to simulate, you want to see your results on the pixel data. Then you can see the diagram per subdomain. So blue pixel diagram subdomain, diagram per subdomain, electrode pixel, blue pixel, electrode, green pixel, red pixel, boundary condition. Also at each voltage wise, potential applied on boundary condition, age, blue pixel on bottom electrode, voltage equal to 0. So based on 0 voltage, you can see your pixel, blue pixel data characteristics, because this type of geometry box that pixel were created. So at 0 volt, you can see these all characteristics. Either you want to see the potential, so I double click on this potential. For bottom electrode, you can find the potential. If you want to see for top electrode potential, this is for top electrode. Source current density for the top electrode, ohmic losses for top electrode, you can also zoom particular region so that you can visualize it properly. I can scroll it and make it on the home so that I can see the ohmic losses top electrode and with the graphical representations so that you can identify and calculate, because this losses and this average or scaling window is there, scaling line is there, which can help you to find the losses due to the top electrode. Similarly, for the ohmic losses, bottom electrode, because top electrode is different and bottom electrode is different. And this is all source power at top electrode, total power at top electrode, this is total power at top electrode, in plane current top electrode, in plane current at bottom electrode, potential difference between top electrodes. And you can publish your data accordingly. You can create your type of geometry. So these are all data at 0 voltage rising. You can see there are multiple graphs are plotted at 0 volt, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. All the graph which I have shown you just now on different voltage rising, multiple output file is generated from 0 volt to 5 volt with 0.1 increment. If you want to see your data at 1 volt, I can double click on it. You can see this is data and with scaling layer. Similarly, click on is at 1 volt and find it and calculate the value of your particular that pixel. The geometry may be different. You can create your geometry according to your convenient. You can import or take the inbuilt geometry builder and find its characteristics. You may take different other conditions. Similarly, this is for only blue pixel characteristics. If you want to plot on other characteristics on other pixel, then you can also able to plot. So this is blue pixel on bottom electrode, potential on top, and you can also see the total device current, ohmic loss, top electrode, ohmic loss, bottom electrode, in watt, source power, total power, electrode area, luminosity. So that's why this all are there. So that's why this result window will help you to show all these things. I would like to take another example that may clarify other maybe doubt. So I click on this import from GIF. Let's say take another tutorial. I can take optical pixel crosstalk as an example. This is one optical crosstalk example where we have taken the optical crosstalk input parameters. So where the layer thickness, encapsulation layer, and their all input parameters are defined. Let me run the job because it is for optical analysis, not for electrical or thermal. Now simulation is running. You can see the ray tracing analysis for optical crosstalk is going to be performed. Now the simulation is completed and results window is enabled. So I can click on this polar plot theta pi with sum over all xy coordinate. So this is polar graph where irradiance is calculated. So positive theta, if you want to see the negative theta, it is also generating the plot at negative theta polar plot. This is at negative theta value irradiance. Similarly, all other xy plot for top emitting, bottom emitting, far field, color plot, all are there. This is at xy plot with top emitting. So which pixel it will calculate? It is a far field color plate is there. You can see the surface with the edge, surface with the wire frame and other. You can see also the movable detector, sample array on different wavelengths, ray tracing wavelengths. This is detector 3D view. You can see this is detector 3D view where this is called pixels. This 4 is called pixels where uppermost or detector width, detector height, that can be seen. And this is sample array. How the light will get on the top for optical analysis, how the light will enter on the device and it will reflect from the device. So that study need to be done. So this is detected wavelength, at what wavelength you are getting the bad or detected, which one is called bad wavelength, which one is called the killed wavelength, which one is called the absorbed wavelength. So accordingly you can see the killed, absorbed or detected wavelength regions. Now similarly I want to take another example These are all FAT-FOSS LAOSS integration is also possible. Full PV module simulation, OPV simulation example, electrical AC simulation, basic OLED without crosstalk, basic OLED with thermal applications, crosstalk with different sections, interconnected series shell, solar concentrator, uniformity. So let's suppose you want to simulate some different OPV let's suppose a series interconnected cell for PV devices. You can see this is a multiple cells connected in series. That's why this is geometry. This geometry. I can show the geometry and run the mesh. This is mesh which is generated in triangular form. This mesh. And this is different like device electrode type, ohmic type or other type. Accordingly, it is selected the required input parameter, steady state AC and excitation frequency we can set. It is a type of electrode where the electrode position is defined, bottom side or top side, and boundary condition. This is the boundary condition that need to be seen. You can see the red color represent the boundary condition here. This red one. For top and bottom, and this sweep again it is taken the voltage potential from minus 0.2 to plus 2.2. This time from negative biasing to positive biasing. So minus 0.2 plus 2.2 with 0.2 increment. So minus 0.2, 0, 0.2, 0.4, 0.6, 0.8, 1. Like that it will simulate and show your output. So let me run for this particular example. Simulation is running. It is calculation done and the results are generated. Total device current, total ohmic loss, bottom ohmic loss, source power, total power, and if any subdomain results are there, it will also display. Now you can see that different potential applied boundary condition results are there at 0 volt, minus 0.2 volt, 0 volt, 0.2, 0.4, 0.6, 0.8. So different biasing, it will plot your results. You can see this is a graph for the solar concentrator. And find the concentration is automatically calculated. Electrode area, total power, source power, and solar cell data can also be collected if it is there. This is difference. Now you can see at 0.2 volt. This is solar cell characteristic data. Maximum power point is calculated. Maximum power per area, open circuit voltage, short circuit current, fill factor, linearly interpolated value, and SP line interpolated value. Accordingly, 0.2 volt the data is calculated. If you want to see this data at 0.4, the data will become change. Something may be difference. So different voltage applying biasing, the maximum power, fill factor, open circuit voltage, or whatever it is, it will change it. You can see the fill factor at 0.4 is 4.5. If you want to see at this value 2.2, it may be something. If it is changing, then it will reflect here. If it is not changing, then maybe it can be same value. So these are all device characteristics output, and some brief idea, presentation and demonstration is given. This is command line, command log window. If any error is there during the calculation or how much time it's taken, that will display in this command log output file. It's a calculation log tab where once you will click on it, it will show which equation, how much time, or how the job is done. Is it the device parameter got converged, or how the convergence accuracy. So that's why this convergence simulation result will show the output, all your output, and project property will give as a input. This is input, this is calculation log, and this is output. These are three major important. In the property project, geometry and meshing is the important, then device input parameter, electrode, boundary condition, and optimization by swapping the parameters, and software will do the calculation in each value. So basically this device can help to overcome the losses, and it will simulate the large area, PV module, LED, pixel, crosstalk, or whatever other application you want to simulate. You can see there are a lot of other options are there. These all examples are available already. This is hexagonal metal grade example. Let me run it. If you want to see the defect, you can see the defect option is also there. You can enable the defect, number of defect you can enable, seed for the defect width, defect height. So defect can be increased, or predefined geometry, radius, metal grade fingers. Now I want to run it. Simulation is running, full Newton solver is executing, calculation is done. You can see the simulation is running on the bottom. If you want to kill it, the simulation can also be run. How much memory, how much percentage the simulation is done, or CPU is utilized, that will show here. So you can get to know about the progress of your simulation. And this is linearly interpolated data of maximum power point, maximum power per area diagram, fill factor data, open circuit voltage. So linearly and spline data is there, and you can plot all the characteristics according to the convenient. So from my side, I have given the overview about the tool. So if participants have any questions, I request you can unmute your mic and please put up your questions. So thank you very much from my side. I have tried to explain a lot of things, but once you will explore the tool, then you will have a much clear idea. And if need more in detail, then we can also have a more discussion in future.